Welcome to the experiment 2 of CSE 350 lab. In this lecture, we will be simulating direct transistor logic gates or DTL gates. Direct transistor logic is the direct descendant of digital logic. We use DTL because DL system can't design all types of gates. For example, the inverter discussed in experiment 1. In direct transistor logic system, logic function is done by the diode network and the amplifying function is done by transistors. In this experiment, we will be simulating a two-input NAND gate. A NAND gate will have low output when both inputs are high and will have a high output in all other possible combinations of the input. Now we will look at all possible combinations of input for the circuit shown in this slide. When both inputs are low, in this case, the two diodes will turn on. There will be forward biased. So this point Vp will have a voltage equal to 0.7 volt. But to turn this transistor Q1 on, we will need approximately 2.1 volt on this point Vp. So why 2.1 volt? Here we can see two diodes D1 and D2. We know to turn on a diode or to make it forward biased, the voltage difference between the anode and cathode has to be 0.7 volt. And similarly, this transistor Q1 has two diodes. One of them is a base emitter junction. So this will have a voltage drop of 0.7 volt too. So 0.7 volt voltage drop is equal to 2.1 volt. So to turn the transistor on, Vp has to be 2.1 volt or greater. Since when both inputs are on, Vp has a voltage of 0.7 volt, that means it won't have enough enough voltage to turn the transistor on, so the transistor will be in cutoff state. So no current will pass through the transistor and the output Y will be equal to 5 volt or logic high. Now second condition is when one of the inputs is high, the other input is low. Let's say A is high or 5 volt and B is logic low or 0 volt. In this case, the diode DA will be reverse biased, so it won't conduct any current, but DB will be forward biased. So Vp will still have a voltage of 0.7 volt approximately. Which is still not enough to turn the transistor on. So it will be in cutoff state and the output will be equal to 5 volt. Same case when input A is low and input B is logic high or 5 volt. The output will still be high. Now the last case, when both inputs are high. In that case, input A will be logic high or 5 volt and input B will be logic high and 5 volt too. Now diode DA and DB will be reverse biased. So they won't conduct current. So now BP will have a voltage of 2.1 volt. that is equal to drive the transistor on. That means the base emitter junction will now be in forward bias condition. Since both junctions of the transistor is forward biased, it will be in saturation. And we know in saturation, the voltage difference between the collector and emitter voltage is almost 0.1 volt. So we can say the output will be logic low or 0. So we can tabulate the values from the previous slides in this table. So we can see this is the truth table of a NAND gate. So the circuit on the right hand side is the detailed implementation of NAND gate. If you actually look at the circuit carefully, it consists of two circuits from experiment 1. This portion is the diode logic AND gate, and this is the inverter or NOT gate. So the N plus AND and NOT gate both are combined to form a diode transistor logic NAND gate. Thank you everyone.